Welcome to The Explainer. Today we're going to break down a really fundamental concept in modern software, object-oriented programming, or OOP for short. It's a way of thinking that powers, well, pretty much countless applications you use every single day. Okay, so to really get why OOP was such a huge deal, we kind of have to go back in time a little bit. We need to look at the world before it existed and see the programming headaches it was really designed to cure. So, in the old world of what's called structured programming, everything was all about the verbs, the actions, the algorithms. Data was just this passive stuff that got passed around from one function to another. But then OOP came along and just flipped that whole idea on its head. It made the data the star of the show by packaging it into these neat, self-contained things called objects.
And you know what? That difference became absolutely crucial as programs started getting bigger and more complex. The old structured way just started to buckle under the weight. With data being passed around so freely, it was like having this one giant swimming pool of information that any part of the program could just jump into and change, often completely by accident. There just wasn't a good way to protect data from being meddled with.
So this wasn't just about, tidying up some code. Nope, programmers needed a completely new way to even think about building software. And the solution was a revolutionary approach, thinking inside the box.
And here's the really cool part. OOP didn't just throw the baby out with the bathwater. It kept all the best parts of structured programming, but it totally shifted the focus. So instead of writing a long recipe of steps to follow, programmers started creating these little digital models of actual things from the real world. So how does it pull this off? Well, in OOP, you bundle the data and the functions that use that data together into one self-contained unit. This means the data is basically hidden away. It's protected from accidental changes, which leads to two of its most powerful features, something called data encapsulation and data hiding.
Okay, to really let this sink in, we're going to use a super simple but really powerful analogy. This is where all those abstract ideas of OOP start to become concrete and just click. All right, first thing you need to know about is the class. The best way to think about a class, it's the blueprint. It isn't the actual house, right? It's just the detailed set of instructions for how to build a specific type of thing. And then, using that blueprint, we create an object. An object is the actual thing. It's the house you built from the blueprint. It's this self-contained component with its own properties and behaviors, all built exactly according to that class blueprint. Okay, let's make this super concrete. Imagine for a second we're building some software, say a pet management system. The very first thing we'd need is that blueprint, our class, for a dog. So our dog blueprint, it needs two key things. First, you've got its characteristics. Programmers call these properties, things like its breed, its age, its color. And second, you've got its behaviors, what programmers call methods. This is all the stuff a dog can do, like eating, sleeping, and sitting. Makes sense, right? And check this out. You can see exactly how that blueprint idea translates directly into actual code. Now, don't worry about the specific syntax here. Just notice how the class is named dog, and right inside it are those very characteristics we just talked about. Its breed, size, age, and color. That's it. That's the blueprint, just written in a language a computer can understand. And this is where the real magic happens. Using this one single dog blueprint, we can create a whole park full of totally unique dogs. We could make one object for a little white Maltese who's 2 years old, and another one for a big brown German Shepherd who's 5. See? Same blueprint, but different data gives us completely unique objects. So this whole way of thinking, building things with objects, it unlocks some seriously powerful advantages that make programming way more organized, reusable, and just easier to scale up. Yeah, this whole approach is built on 4 main pillars, or as I like to call them, it's 4 superpowers. We've got encapsulation, abstraction, inheritance, and polymorphism. Now, getting these is the key to really understanding OOP, so let's break down what each one actually lets you do. Okay, first up, encapsulation. This is that core idea of bundling data and the methods that work on that data together inside an object, like a protective capsule. It goes hand in hand with our second pillar, abstraction, which is really just about hiding all the messy internal stuff and only showing what's essential. Think about it like a car, right? You use the steering wheel and the pedals, but you don't need to be a mechanic to drive it. Encapsulation is the trick that makes that kind of powerful simplicity happen.
All right, next up is inheritance. And honestly, it's pretty much exactly what it sounds like. It lets a new class automatically grab all the properties and methods from a class that already exists. This is a huge deal for reusing code. For instance, you could have a golden retriever class that inherits all the basic dog stuff, and then you just add its own unique methods like retrieve.
And that brings us to our final superpower, polymorphism. It's a fancy word that literally just means many forms. What it means for us is that different objects can respond to the exact same command, but in their own unique way. So if we had a command called make sound, a dog object would bark, but a cat object would meow. Same command, totally different, but appropriate results. So I know these ideas might feel a little bit abstract, but they really come to life when you see them in an actual programming language. And to see OOP in action, there's no better place to look than a language that was basically built from the ground up on these ideas, Java.
Now, Java's known for a lot of things, but its entire philosophy, its very soul, is built on OOP. Like our source material highlights, in Java, practically everything is treated as an object. It's not just a feature, it's in the language's DNA.
And this object-first way of thinking, it shapes every single part of the language, even something as basic as how it stores data. You can almost think of it like Java having different levels of privacy for its data. Some data is super private, kept inside a single action. Other data belongs to a specific object, like our dog's age. And some data can even be shared across all the dogs we create from that one blueprint. It's all about controlling access, a core OOP idea.
And this table here, it breaks it down really nicely. You've got local variables. Think of those as temporary thoughts. They're there 1 second and gone the next. Then you have instance variables. Those are like memories unique to one specific dog, such as its name. And finally, you have static variables. These are like a breed standard, a core trait shared by every single dog created from that blueprint. So when you pull it all together, you start to see that object-oriented programming isn't just a style. It's this incredibly powerful, structured, and really intuitive way to tame complexity. By building our software out of these digital models of real-world things, we sparked a revolution that honestly made the entire digital world we live in today even possible. Which leaves us with a pretty cool question to chew on for the future. Objects helped us model the world. What's going to be the next big idea that helps us model the universe?